All right, let's get right into it. We're going to break down the fundamental building blocks of, well, everything, our entire universe. We are starting from scratch, looking at the actual code that writes reality itself. So let me kick this off with a pretty wild question. What if everything you know, the chair you're sitting on, the air you're breathing, even you, was all built from just three tiny fundamental particles? The crazy thing is, that's exactly how it works. Let me show you. So our first stop has to be inside the atom. And I know what you might be thinking. Oh, atoms, high school science class. But trust me, this isn't just a science concept. This is the basic code of the universe. It's the alphabet that every single thing is written with. And here they are. This is it. This is the entire toolkit. You've got your positive protons and your neutral neutrons all packed tightly together in the center, which we call the nucleus. And then, buzzing around the outside in these orbits are the negative electrons. They're so incredibly light that their mass is basically nothing in comparison. 3 particles. That's all it takes. Okay, so wait a minute. If everything is made of the same 3 particles, how do we get all this variety? How is a piece of gold totally different from the oxygen we breathe? Well, it all comes down to the atom's personal identity card. And this, right here, is the most important number on that ID, the atomic number. It's simply how many protons an atom has. That's it. An atom with 6 protons is always carbon. One with 8 protons is always oxygen. You change the number of protons, you literally change the element. It's that absolute. So if the atomic number is the ID, the mass number is basically its weight. It's super simple. You just add up the protons and the neutrons, the 2 heavy particles that are in the nucleus, and that gives you the total mass. We pretty much just ignore the electrons for this because they're just too lightweight to even matter.
Now this is where it starts to get really interesting. What happens if you keep the number of protons the same, so the identity doesn't change, but you mess with the number of neutrons? Well, then you get an isotope. It's the same element, for sure, but it has a different weight. Kind of like having a heavier or a lighter version of the exact same thing.
And this is the perfect example. Take a look. Both of these are carbon atoms, no question, because they both have 6 protons. But carbon-14 has a couple of extra neutrons. That not only makes it heavier, it also makes it unstable, or radioactive. And yep, this is the exact same carbon-14 that we use for carbon dating, figuring out how old ancient artifacts are. Okay, so we've got all of these different elements, each with its own unique atomic number. There has to be a way to keep them all organized, right? Well, there is, and it's probably the most famous chart in all of science, the periodic table. It's like a master atlas for every atom in the universe. Let's just do a quick little tour. The columns going up and down are called groups, and here's the secret. Elements in the same group act in very similar ways. So way over on the left, in group 1, you have the alkali metals. These guys are super soft and just love to react, sometimes explosively. Then you've got group 7, the halogens, also very reactive. And way over on the far right, group 8, you have the noble gases. They're the cool kids. They're chemically inert, they don't react with anyone. But why? Why do they act so differently? Well, the whole secret is in how their electrons are arranged. And believe it or not, it all follows this one surprisingly simple rule. The electrons fill up in layers or shells around the nucleus. The first shell can hold 2, the second can hold 8, and the third can also hold 8. Okay, pop quiz time. Let's put that rule into action. Sodium's atomic number is 11. That means it has 11 protons, and so it also has 11 electrons to balance it out. Using that 2-8-8 rule we just saw, how would you arrange those 11 electrons? Take a sec to think about it. The answer is 2-8-1, right? 2 electrons fill up the first shell, 8 fill up the second shell. And that leaves just one lonely electron all by itself in that third outer shell. And that one single electron on the outside, that's everything. That's what puts sodium in group 1, and it's the reason it's so incredibly reactive. It is desperate to get rid of that one electron. So we have all these theories and all these rules that seem to govern how atoms work. But this is science, right? How do we know any of this is actually true? Well, let's look at a couple of simple but really powerful experiments that prove it all. Okay, check this out. In this classic experiment, you take 2 totally clear liquids, seal them up in a flask, and you weigh the whole thing. Then, you just tip the flask so they mix together and bam, a solid white substance appears out of nowhere. It looks like magic. But then,
You weigh the flask again, and the mass is exactly the same. Not a single tiny bit has changed.
And what that simple experiment proves is one of the most fundamental, rock-solid laws of our entire universe. Matter is neither created nor destroyed. The atoms just rearranged themselves. They formed something new, yeah, but every single atom that was there at the start is still there at the end. Nothing's lost.
And hey, remember those super reactive group 1 alkali metals we talked about? Well, this is what happens when you just drop them in water. First, they're so light they actually float. Then they just go nuts, fizzing like crazy and releasing hydrogen gas. And the further you go down the group, the more intense it gets, until you get to potassium, which just erupts in this incredible lilac-colored flame. That's chemistry you can really see. So we have our atomic building blocks. We understand the rules they play by. Now let's see how they actually come together to build all the stuff we see around us every single day. Basically, everything can be sorted into one of 3 buckets. First, you have an element. That's the pure stuff, just one kind of atom, like a bar of pure gold. Then you have a compound. That's when different elements are chemically bonded together, like H2O, water. And finally, you have a mixture. That's when stuff is just jumbled together, but not actually bonded. Think sand and salt mixed in a bucket.
And the cool thing about mixtures is that since nothing's actually chemically stuck together, you can usually pull them apart with simple physical steps. Take that sand and salt. You just add water, and the salt dissolves. Then you pour it through a filter, which catches all the sand. Finally, you just boil off the water, and boom, your pure salt crystals are left behind. Easy.
So we've covered the basic particles, the rules of their identity, and how they come together to build our world. It's a universe built on these really elegant, predictable laws, which leaves us with one last kind of mind-bending thought to wrap up on. If these are the rules for how things combine, what happens when we decide to force them apart? But that's a story for another time.